Welcome to the last talk of this week. And so today we'll have the pleasure to hear about the latest developments with SDPB by Walter Landry. Go ahead, Walter.
Okay. All right. Well, hello, everyone. Yeah, I'm going to talk about a lot of numerical work I've been doing on the outer approximation, approximating objectives, and all the various enhancements to SDPB. So I'm going to do it in reverse order. I'm going to start with enhancements. So these are some fairly minor things. I added some stopping conditions. Sometimes when the primal and dual steps get very tiny, it will eventually stop because you run out of iterations, but if you don't want to wait that long, you can add these parameters, and then it will stop sooner as soon as it figures out that it's probably not going to get done. I also cleaned up some default output, and I fixed some minor bugs, but the big thing that I changed was that I changed the output format of SDP to input and PVM to SDP. So if you think of yourself as a little human wandering in a maze, and you know how to work this system, so you know where the cheese is. Well, unfortunately, I moved your cheese, right? So it won't affect most of you, but it will affect some of you if you're sort of fiddling with this internal format, which I know some of you are doing this. Some of you do all sorts of things. So, anyway, I changed the format where essentially SDPB talks internally to itself. So the output of SDP to input and the input of SDPB. And the reason I did this was because I was running, we were running into problems with corruption when we had a whole bunch of inputs on large, flaky, parallel file systems, and you would sort of randomly get Unicode characters in your numbers. And the nice thing about the new format is that it has a built-in checksum. It's also a single file, so there was also a problem when you would make too many files, and then some file systems aren't happy with lots and lots of files. So this fixes that problem. Like, you have plenty of space, but the number of file inodes you have is limited. So it should be transparent to sort of most ordinary users. It's really only going to be the power users who are mucking around with things sort of a little more internal that may see a difference. The format is fairly simple. It's a zip file with JSON files inside, and actually you don't even have to make it a zip file. I made it so that you can sort of read any archive format. But for most people, you shouldn't notice. But if you run into a problem, now you know what's causing the problem. And if you have any questions, as always, you should ask me. So that's most of the straight enhancements that I've done to SDPB. I'm also, one of the things I'm planning on doing very soon is making a new spectrum extraction tool. So right now we have this Python script with spectrum.py. This sort of works. It's kind of a pain to install, has different dependencies. It only takes some inputs and not other inputs. So what I'm planning to do is just make it sort of a spectrum extraction tool that can take more inputs, and it'll all be bundled with SDPB. And so, and if you, for some reason, write your own inputs to SDPB and don't use these programs, it's fairly simple to write what is needed for spectrum extraction by just essentially giving functions evaluated at Chebyshev zeros. So now I'm going to talk about one of the new programs that I've written, which is Approximate Objective, Approxobjective. It's included with SDPB, so you can use it at your leisure. And the idea is that if you have an existing semi-definite program, you can, and you have another one that is close to it, you can use the solution from the first one to compute an approximate objective for the second one. You don't get the solution, you just get the objective, right? And so if you write, if you can specify if you the semi-definite program is specified by these quantities B, C, B, and A. You can do a perturbation dB, dC, dB. A you probably shouldn't vary. I mean, in principle, I could write it so it handles that, but there's not a strong reason to do that. Anyway, so the setup is you have an SDPB, an SDP, and you have a perturbation. All right. Then you can write the normal objective in terms of these three terms. And actually, all of these terms are the same. So like this and this cancel out, but also this and this cancel out. In case you're used to a slightly different form. So you can take a derivative of this and a whole bunch of things cancel out. And so you get a term like this. And then you can take another derivative, essentially, or variation, as it were. And you get something like this, all right, with all sorts of cancellations. And for the first order terms, this only uses dB, dC, and d capital B, which is what you gave to the program. And so it's very fast to compute. It has the original solution. It has x, little y. So it can just compute this very quickly, no problem. These terms have dy and dx, and those are implicitly defined. And essentially, you have to do some work that's basically equivalent to a single SDPB iteration. So it's not a lot of work. It's certainly a lot faster than computing a complete solution, but it is like not running on your calculator kind of thing. It's more like running on a real machine, but it finishes relatively quickly. And the result is going to be second order in the variation in B, C, and B. And if you, however, I want to stress that if you vary B, C, and B by changing some underlying parameter, the answers may not necessarily be accurate to second order in this underlying parameter. Anyway, there's I wrote a whole bunch of documentation about how to use it in the usage file. The basic workflow that I'm envisioning, which is that you run SDPB, and then after you have a solution, you run this approx objective, and then you can get as many objectives as you want. All right. So
I'm sorry, but
yeah.
Shouldn't you cite a Navigator paper here?
Sorry, yeah, it's I cited it in
yeah, but
in
we are grateful that you realized this algorithm, but we came up with this algorithm, so we would like to be cited.
Okay. Well,
not everybody is going to read the docs.
It's on the main page. It's in the README.
Okay.
For the for SDPB. So it's on the front page in attribution. So.
Sorry, Walter, I did not understand this comment about the parameter. You mean like that phi might not be linearly related to B, C, and B? That's
right. Okay. If it's linear related, then you'll get a nice convergent answer. But if it's not, then it's not clear that you'll get second order in phi. If you only vary B, C, and B directly, then you will get second order in B, C, and B.
Very good. Okay. Thank you.
All right. Okay. So
it's not so hard to also include the change in A, right? Yeah.
No, it's not hard. Just it's not much call for it. So but if there is call for it, I can certainly add it.
Yeah, we have to think about this. I mean, it's, for example, changing the gap. That would be a change in A. It's not just, if you change the basis of polynomials.
Yes.
You would not want to do that ever, I think.
Right. So is it?
To do. But there's one small other thing, which is the origin, what you call x equals 0.
Right. Wait, x or delta?
Depends on which paper.
Okay.
But yeah, delta the gap. And if you change the gap, then you want to change A. So
okay. It would not be hard to add A. If that is certainly to first order. It wouldn't be hard. I don't remember the second order terms.
I think it's still a single iteration,
Okay.
but David hadn't worked it out yet.
Okay. Okay. All right. So all right. So that's approximate objective. So that's one new tool. The second new tool, which is what I've been spending most of the time on, is outer limits. And it's essentially another tool to solve semi-definite programs. And it uses a different method called the outer approximation. It's now included with SDPB, so you can try it out. So I'm sure a lot of you have seen this many times, but I'll just go over it again. Just we consider a very simple linear programming problem with two functions. We want to maximize this minus y such that this is always greater than 0 and for all delta greater than 0. But we want minus y to be as big as possible. And this is the dual problem. And it's also equivalent to optimizing a different problem, which is a primal problem, where you're minimizing something. So you have you can minimize or maximize things, and you'll end up in the same place, right? And when you're in the same place, that's essentially when you found the solution. So a good stopping threshold is when the gap between the dual and the primal objectives is small. Right? And the way that SDPB does this, it solves this whole thing, is by it requires you to approximate the functions with polynomials. So your answer is only good as your approximation, which to be fair could be pretty darn good. So but you do have to do that yourself. And using that, SDPB can essentially construct a matrix that, if it only has positive or 0 eigenvalues, it implies that the functionals are positive everywhere. Right? The problem is that when the objective is optimal, when you've gotten to the solution, many of these matrices have eigenvalues that are 0. And as you're getting closer and closer and closer, the eigenvalues get closer and closer to 0. And the problem is that you have to invert these matrices as you are solving the problem in order to take the next step as you get closer and closer and closer. And this causes all sorts of numerical difficulties that we're very familiar with. And SDPB just bulldozes over all of this by just using arbitrary precision arithmetic. Unfortunately, arbitrary precision arithmetic is quite slow. It's hundreds of times slower and uses an order of magnitude more memory. Right? So the outer approximation approaches this from a different way. The idea is essentially to, instead of worrying about the functional being positive everywhere, we're only going to ensure in a few places at first, right? So you have some constant constraints, not polynomial constraints, at a few starting points. And so here I have 0, 1, and infinity. And we're just going to enforce that the functions are positive at these 3 points, and then we'll optimize y. So we compute an optimal objective given the setup. In general, the constraints can be matrix constraints. So I needed a semi-definite solver, and I had one called SDPB. So I just ended up reusing a bunch of SDPB routines. So you have this setup, and you've with these 3 points at first, and you get a solution for the optimal value, and it's going to be negative in some places, but you're not really sure where because you haven't. So to find out where, what we do is we construct essentially an adapted mesh. We look at the function, and we add points essentially where the curvature is large, and large is a little fuzzy here. But wherever the function is varying a lot, we add points.
Only where it's negative, or
no, we haven't gotten to the negative part. This is just making sure that we capture all the variability.
I see.
Now, next thing is we find the negativity. So we have this basic mesh in place. And so we have a bunch of intervals with points inside. And then we compute a quadratic approximation to the functions inside each interval, right? And that gives us a minimum value inside each interval, right? So if the minimum is not in the interval, so in this case, the minimum is going to be outside of these 3 points. We just skip it. We don't try to add more constraints. But otherwise, we add a constraint at the minimum point if the functional is negative, but not like just barely negative. If it's like minus 10 to the minus 300, well, that's probably just arithmetic precision problems, and we call that 0. But it could also be that it's positive, but the quadratic approximation is so terrible that it could allow it to be negative. So we have, I mean, usually it's when it's negative, it's negative, but you run into these weird corner cases. So I had to fix for those kind of special cases.
Do you evaluate the functional at the minimum of the quadratic approximation?
I do not. What I do is I have this quadratic approximation, and I compute the quadratic approximation, which gives me the minimum, but I do not directly evaluate the functional at the minimum. This is just for adding constraints.
Yeah. But you have an estimate somehow for the error in the quadratic approximation.
Right. Right. So like the difference between a linear and quadratic approximation will give you some sense of the error.
I see.
Yeah.
Okay, thanks.
Okay. And this seems to work well enough, this procedure. It doesn't really take very much time. It seems to be robust enough to find all the zeros for this relatively small number of problems that I've tried. And one of the reasons that I'm giving this talk is that I want more people to try this out, find out where it breaks. I'm actually pretty confident in this part. It seems to work pretty well. So yes, so now we know where all the negative parts are, and we can add a constraint essentially right at the minimum point, right? And then we compute a new solution. And we repeat this enough times, eventually we'll run out of points. We won't be able to find any more negative points. And at that point, we'll say we have a solution. And it turns out this is also slow, all right? And because you have to do this iterations many, many, many times. And even with constant constraints, it just turns out to take a long time.
What do you mean with constant constraints?
So, so these are all constant constraints. They're not polynomial constraints. I'm not saying that the
because you mean you add constraints only at points, you're saying?
Yeah, only at points, yes. So, okay. All right.
But when you say it's slow, you mean, like, for example, for this toy model example that you showed,
orders of magnitude.
If you run it with usual SDPB or with this method, what's going to happen?
So it will be, yeah, like orders of magnitude slower.
Okay.
So something like that. So it'll take 10 seconds instead of 1/10 of a second or something like that. So.
Walter, do you know? Sorry. Do you know if on the previous slides, if you can, we can say that we have a solution? Is that rigorous? Are we done?
So I can say that the function. I can say that the functional is positive to some error.
And that the solution is optimal?
And well, yeah, the gap is as small as you make it.
Or you measure the duality gap?
Yeah, well, the duality gap is the stopping condition.
But here you don't have a primal matrix.
But no, you have a primal too.
Oh, I see. Okay, fine.
So,
right.
Okay. So anyway, so this is slow. So one of the things that I did was at the beginning, we don't need a super precise solution to the problem because we're gonna throw away the solution right away anyway, because we're gonna add some new constraints, right? So we have very, very loose constraints to duality gap at the beginning. Like essentially it has to be feasible at the beginning. That's it. Instead of like super precise and super close, right? So you compute this approximate solution to the approximate problem and look for negativity. And you do that until you run out of points. And then you reduce the threshold. And then you look for more points, and then you reduce the threshold again. And you keep doing that until the duality gap is as small as you want. So let's see how this works. This is the toy example. This is the first solution. As you can see, that it is positive everywhere, but it's really not optimal. Okay, and that's because the duality gap is essentially large. So for the second iteration, we reduced the duality gap, and then we got something that looks a little more optimal. Okay, and so these blue circles are the initial points, 0, 0.1, 1, and I also have one way at infinity. And so it adds 1 at about 1.04. And then let's see what happens in the next iteration. So it computes a solution, and it's positive everywhere, but it's not optimal. It can't find any negative points, and so it reduces the gap again. And then it finds this solution, and then it says, oh, well, actually, wait, no, this is actually negative, so it adds a point right here. And also, one of the things I want you to notice is in the previous slide, this is, goes from 0 to 10. In this slide, it goes from 0 to 10 to the minus 3. So it's many orders reduction in magnitude, even with just these few points. And I've really zeroed in here. This goes from 0 to 1.5. This goes from 1.02 to 1.06. Right. So now we have this at the fourth iteration. We have a new constraint, and the fifth iteration I'm not showing because I've shrunk the I've shrunk this to quite small. This is 10 to the minus 9 now, and the solution for iteration 5 is actually way off at the top. It's disappeared. So then we reduce the gap again, and we get iteration 6, and reduce the gap again, and we get iteration 7. And okay, now we got to add a new point. We get iteration 8, and then we're done. We've got a solution.
Can I ask something?
Yeah.
Sorry, I got confused. So what's the problem that we wanted to solve? Because are you saying that in iteration 1 you found a functional that already excluded the point?
So in iteration 1, I found something that is feasible but not optimal.
It's an optimality.
Which problem? Feasible for the dual problem, right? Which is the one that you're solving, right?
It's feasible for, yes, it's feasible for the problem, this toy problem that I'm talking about.
Yeah. Yes. Sorry. And that is in SDPB language like the dual problem.
Yes. Yes. I mean, I believe it's feasible for primal and dual for this. So, okay. So that's sort of the way that it sort of converges on the solution.
I have a question.
Yes.
So when you go from one iteration to the next iteration, I guess internally you hot start from the output of the previous iteration, right?
So some of them you can hot start better than others. So if you're just going from like iteration 6 to iteration 7, all you're doing is reducing the gap, and so that's just like continue the solution, right? Like don't actually stop yet. So it just keeps going and keeps reducing the gap. To go like from 7 to 8, you've added a constraint, so the linear system has changed, and for that I can reuse the essentially y, little y, but I can't reuse little x because the dimensionality of x has changed.
Okay, I see. But so all these iterations are automatically performed in the background, right?
Yes. Yeah. There's an iteration. Yeah. Yeah. I mean, it prints out things, that sort of thing. But
Yeah.
so you can see, for example, the gap the gap threshold as it decreases, and as it adds points, how many points it's added each time, that sort of thing. So,
I see. Thank you.
So what text do you put initially for that new entry?
sorry, what?
So
What
you
text?
have a new block for that pointer, right? What initial value you put for that new block?
So I have an initial. I mean, I start with the initial matrix values and an initial guess for little x, which is 0. So it's just like starting SDPB from scratch, except that I have a solution for little y that I start with.
Okay, thanks.
Okay. All right. Okay, so there's this, this works okay. There's no ill-conditioned polynomial matrix, so I can reduce the precision somewhat. But it turns out the input, if you give it bad input, you're still gonna have problems. If you put weird scalings in your functionals, which everyone does because it's hard not to, you can inadvertently cause a lot of numerical problems. So one of the things I did was I condition the matrix before I actually try to solve it. So we have this capital B matrix, which is evaluated at all the initial points, right? And so this B is going to change from iteration to iteration, but we're just going to look at the initial points for right now, all right? So this is, we have F1, F2, F3, evaluated at delta 1, delta 2, delta 3, all right? We can compute the singular value decomposition of B, right? And so then you have this U sigma V transpose. U and V are orthogonal matrices, and sigma is a diagonal matrix. Though it's U and V are square and sigma is rectangular. So it's mostly 0 and there's a diagonal right at the top. And with that decomposition, you can rescale everything. And things become sort of more nicely behaved. Everything becomes kind of 1. And there's a few more details I haven't gone into. But if you do this, then you can reduce the precision requirements even farther. And I'm not sure where I would go after this, as far as I can figure out. And also, as a side bonus, it seems to reduce the need to scale these initial matrices, because everything is about 1. You don't have things that are sort of enormously huge anymore.
I'm sorry, so this would make sense even in the usual SDPB, the step that you're describing?
So in the it wouldn't help so much with the usual SDPB, because the precision requirements come from the singularity of the matrix as you go along, not the sort of the initial setup. And this is one of the things I talked about a bit at.
I remember. But since you are saying that in the usual SDPB we had this matrix scale.
Yeah.
Okay.
Yeah. Oh, yeah, that might help. Yeah, that might help. It won't help the precision, but it will help. But there's no free lunch.
So if you go back on your previous slide, you have a matrix B, which is very much like the matrix. Oh, the one before that. Sorry, this is very much like the matrix. This one.
Okay.
It's very much like the matrix B in SDPB, right?
It is the matrix B.
Except your points, your choices of the deltas in the matrix B in SDPB are of course the sample points, and
yes.
Here they are the cleverly chosen points where delta.
Yes. Oh yeah. So it might mix up blocks. It will mix up. Well, I'm not sure.
I don't. If it's the same matrix, I think it might be the same matrix.
It is the same matrix. Yeah.
Yeah. I mean, okay. If we stick with SDPB, you could ask whether we can dynamically choose the sample points
So you would still, okay, yeah.
So that you
you
basically have a
can,
matrix B that looks a bit like the matrix that you have here, where the deltas are
right.
roughly speaking the
Um,
minima of the functional. And then do a
Right.
singular value decomposition of that guy. And then if you go to the next slide, you can do the the redefinition of Y and B.
Right.
Everything else.
Yeah. I mean, I think that might. So you can do that. It just, I feel like there's something that's gonna. I don't know that it will help. I guess that's my concern. Because you're still gonna have these singular matrices at the end that you're gonna have to invert. And the only reason that I'm doing this is because I wanted to reduce precision requirements. I mean, this is like a little molehill kind of problem for SDPB, whereas the singular matrix is the giant hill that you have to move with the bulldozer. But I only noticed this because I've gotten rid of the big hill.
Yeah. Yeah. Okay, I see.
Okay. Right. So this seems to reduce the need to scale matrices. Instead of magic numbers like 10 to the 20 or 10 to the 50 or whatever, you can just, I use numbers like 10 or 1,000. Right. But as with everything, there's no free lunch. You can solve this new equivalent system, but SVDs are slow and they take, I mean, I say here it's similar to a single iteration. It's more like maybe 10 iterations, I think. It's not nothing. It's not dominant if you don't do it too many times, but you can't, you wouldn't want to do it every time for every solution. Because B is actually quite big, right? I mean, so to reduce this cost, we only compute the SVD once at the very beginning. So you have this U sigma V from the very beginning, and then you compute a new B prime and Y and whatever from these existing V sigma U, right? And so, when you did this originally, this B prime would be essentially an orthogonal matrix, which is, about as good as you can get. Now it won't quite be as perfect, but it still seems to work okay. And, so now I have a system and it seems fairly robust, but I feel like it could be further optimized, but it feels very problem dependent. For example, when I add a constraint, I only add a constraint like right at the negative, and maybe I should add more points. And I tried that and it made it worse because then each iteration would get more expensive. So maybe I could do something, but as you saw, the scales get really change a lot and things move around. So it gets a little tricky to come up with an automated way of doing this. But in the end, this is what I got. This is one of a problem, which is not a trivial problem that I solve both ways, basically with SDPB and with outer limits. And I use 36 cores. It's solved to a gap 10 minus 10. And outer limits takes about 5 times longer, which is not great. It uses less precision, which is great. It uses a lot of iterations and uses much less constraints. So, I feel like I could, maybe I could make it work better, but it's certainly not better now. And it kind of depends on what you're trying to get out of it. Also, it feels like as you're converging, it doesn't converge kind of as quickly and as SDPB does. And in SDPB, every time you do an iteration, when you're in that zone of convergence, it reduces the gap by a constant amount each time. And for this one, it doesn't really feel like it does that. It feels like, I reduce the gap threshold and then I'd go hunting around for a bunch of new negative regions. And then I reduce the gap again and I got to hunt around and, I eventually get there, but it feels like, there's a lot of this sort of looking for negativity. Also, one of the things I wanted to talk about was sort of how much can you really reduce the precision? And for this particular example, which is not that big, which is not that complicated, just verifying the solution requires a lot of precise cancellations. And so, you know, you could never use IEEE for this because, you know, just verifying the solution will require more than the regular double precision numbers. And I would expect that would be true for a lot of these problems. So, when it comes down to it, this is essentially the pros and cons of outer limits versus SDPB. You don't need to make an explicit polynomial approximation to your functionals, though there ends up being a polynomial approximation because I do it for you, sort of in the internally. You only give it essentially the value of the functionals at Chebyshev zeros, and then I will compute the polynomial for you. It requires less precision. It might scale better. I feel like I need to do more experiments with bigger problems because we have all these tiny little constraints instead of big blocks of polynomial constraints. I could maybe farm all that work out to a whole bunch of cores. So maybe I could use like 10 times as many cores. I don't know, and then it would be twice as fast. But you know, I feel like I haven't quite nailed down the scaling yet. But it is still experimental. It seems to work. It seems reasonably robust, but it's not going to be fast in SVD. So it's really sort of, if you want to experiment and if you want to see if this will work for your problem, then it's sort of ready for that. So, and one of the things that I've been thinking about is maybe I should set up the code to be able to use machine precision, because right now everything's set up to use arbitrary precision, which is terribly slow. And even if you use the lowest precision that I'll let you use, which is 64 bits, this is still going to be a whole lot slower than using this hardware accelerated double precision. So I'm thinking of making like an option to use IEEE, or I could play games with, you know, changing the precision of outer limits as you decrease the gap. I'm not sure. I worry that, I have a precision and then it doesn't work. Then I got to do all the work over again, but with slightly higher, but not too high. You know, there's a lot of fiddling that I could imagine would cause problems. So that's my talk. Let me know if you have any more questions.
Thank you very much, Walter.
One quick question. I'm sorry, I missed the first part. Have you written something up on this? I think it's very interesting, and I would be interested to see it.
There is a manual in the repository, which describes this method in more detail.
Okay.
So if you go to docs.outerlimits.pdf, there's a PDF that you can read, which
it's very interesting. Not surprisingly, it has echoes in solvers that are used in lattice gauge theory, where we find that we use extremely low precision until we get close to the answer. This has huge efficiency advantages.
Yep.
And in fact, one of the reasons that GPUs are good is because they do a lot of very quick, low precision stuff before you have to get real.
Yep.
There, actually, double precision is the endpoint, but it's you've got a
yes.
But nonetheless, the ideas sound plausible, so I'd like to look at it.
Okay.
Right. Very interesting. Thanks.
I can go on forever, but maybe other people have questions.
Yeah, just to make sure I understand, is the calculation in the original Navigator paper the one where you don't need a prox objective because it uses a first order SDP gradient formula?
I believe that the original Navigator paper, only does first order. But okay, I think so Slava knows this better than I do. So
Yeah, it's
But
exactly that.
Approximate now computes both first and second order, so it can do anything. What we did, so I guess there's in Approximate there's probably some option to say if you need first order or
Yes.
both orders, right?
Yes. Yes.
So it can do anything. It's great.
Yes.
But the extra work of doing like about one SDPB iteration, that happens when you want the second order solution, right?
Yes.
Yeah, because otherwise DB and DC and D capital B are just known.
Yes. Yes.
Okay, thanks.
Yeah. No, yeah, that's like on your calculator kind of problem.
So I was wondering, so something that you said. So you said that there is this problem that even to verify that you have a solution, you need a certain amount of precision, and that's because. So can we discuss this? It's because of what? It's because your polynomials have. Yeah, can we discuss that? So what's?
So the problem is that let's say you have a solution
Yeah.
for little y, right?
Yeah.
And so to compute the objective, right, you multiply b times y.
Yeah.
You're going to get a lot of cancellations in that sum. And
but these cancellations they happen. So these cancellations they come from evaluating b at any given delta, or just
this is little b, which is independent of delta, and little y.
So you're saying not to check. You're saying to evaluate the final objective function,
right?
Not to say, because there are two things that you want to evaluate: the final objective function, and you also want to check that your functional is positive everywhere.
Right.
So and both of these things they require.
Well, verifying the functional positive everywhere is gonna be probably even more expensive, but or need more precision. But the even the very simple, just multiply little b times little y, you get a lot of cancellations.
But this problem is in at least in conformal bootstrap applications, it can have a nice workaround provided that you work with functionals in terms of the x variable. So something that has been discussed, but I don't think anybody has tried it because everybody said, well, in the SDPB, this is just one source of the need for the precision, so no reason to try. But so we discussed this, right? So the fact
so you're saying that if you multiply little c times little x, you get something that doesn't have so many cancellations?
No, I didn't mean c times little x. I just meant that the reason why this y that we find in the conformal bootstrap, it has very large coefficients and also a lot of difference between various coefficients. The small entries of this vector and the first entries and the last entries of this vector y are going to be very different in size.
Okay.
But this is partly due to the fact that when we evaluate the functional, we take derivatives with respect to z and z bar of the conformal blocks. And there is nothing particularly, the reason why we take the derivatives with z and z bar is that because it's kind of a little bit historical. And in fact, it's been known since a long time that if instead of taking these derivatives with z and z bar, you do a linear transformation of these derivatives with respect to, basically there are some new different variables x which are nonlinear functions of z.
Right.
So if you write everything in terms of those derivatives, then everything seems to like you seem to eliminate a lot of large numbers. So everything scales. So the derivatives of conformance with respect to x, even though they are just linear combinations of derivatives with respect to z, this simple linear transformation seems to eliminate a lot of disparity between different derivatives. Of course, some of it will still remain, but a lot of it is eliminated. It's been observed.
Okay.
And for example, the following thing is true, that if you just compute a functional in terms of z derivatives, so you find your y in terms of z derivatives, and then you increase the derivative, or you increase lambda, so you compute another functional. So if you work in terms of z derivatives, then this functional, new functional and old functional, they are not going to be simply related to each other. But if you work in terms of x derivatives, then this new functional, you will see that it's the new vector y is going to be basically the same as the old vector y, with a few entries added at the end, but the first entries are not going to be changed at all.
Okay, but wait, so wait, y, little y is changing and little b is not changing, or sorry, little y is not changing at the beginning and little b is changing or not changing?
I was just discussing the variation of y with lambda, which is not something that you've been bearing in this talk.
Right. Okay.
But it's just to show that ideally you would think that in a certain sense, when lambda goes to infinity, the function should converge to something.
Yeah.
But if you look at these vectors as they vary with lambda, then you don't see it at all if you work in terms of z derivatives. But in terms of x derivatives, they do seem to converge. So this just shows that these x derivatives are much more natural.
Okay.
And
so I could, so if you can come up with a setup where you're solving sort of an interesting problem using these different variables, then I can try running it through outer limits, and then we'll see, maybe that'll work a lot better. I don't know.
Yeah, this in principle, this should be very easy to try, because this program 3D blocks, blocks 3D, it actually has an option which outputs blocks in terms of x derivatives. So,
I did a lot of that.
So, you did this, so maybe
there's a whole bunch of coordinates it does. Yes.
Yeah, but nobody tried it because so there's a question whether x coordinate is equal to rho coordinate. No, x is not equal to rho, because it's a question on chat. So because rho eliminates one cut and x eliminates both cuts in the S and T channel. So it's a bit different from rho.
You map both cuts to the plane minus both cuts to the unit disk.
Yeah.
I see. Thanks, Landry.
So that was the coordinate which was used initially in the paper of Duality Mazaj. And in that paper, he observed actually numerically that if you use the spaces for the functional, then the functional seems to converge, at least in some cases that he saw. So this might eliminate a little bit, this might lower down the precision a little bit. But as you're saying, there is always going to be some reducible precision. So
yeah, I don't know. It's very problem dependent, as they say.
Also, in the end, of course, what Slava is proposing is a change of basis in the y space, little y space.
So he's proposing giving me a different setup for the problem, and where things are better behaved. Yeah,
it's just a change of basis in the y space.
I agree. So what I was trying to
to
explain in a complicated way is that there's some God-given change of basis in the y space, which seems to eliminate, which is supposed to eliminate a lot of these cancellations, but not all of them, of course.
Right.
So it will not change the number of iterations required, I think, for outer.
Well,
who knows? Well, okay, maybe you're starting.
No, I mean, it could easily change it. I mean, yeah, you start from a different place.
But one of the beautiful things is that if you extend y, if you make the number of components bigger, which is often what we want to do. We pick a small y and then we make it larger and larger. So in this new basis, y is supposed to change very little. The new components get some values, but the old components more or less stay the same.
Right. So well, and the new components should be about 0, right?
Yeah.
Yeah.
They'll
So you
eventually be
starting with 0 is an excellent approximation. So
for the new components.
Ning Su is raising his hand. Yes, Ning.
Is the adaptive mesh bottleneck? So what is the bottleneck in current?
So the
Which part
adaptive
is the
mesh
lowest?
Yeah, the adaptive mesh is not the bottleneck. That's not a significant part of the time. It's doing all of the inner and outer iterations. So for like this one has 28 outer iterations, and internally SDPB does 20 to 80 iterations. So that's somewhere about 10 times as many iterations as what SDPB is doing. Now, the number of constraints is much smaller, so that helps. But it's still like I said, I feel like let me see. Every time you reduce the gap, you gotta kind of go hunt for negative regions. Okay, you found this one, and then you add a constraint there, and then okay, now another negative region pops up over here, and you end up doing that for a while, and then you can reduce the gap again.
Okay.
And if you just like reduce the gap really small at the beginning, then you spend a whole lot of time on a whole lot of time on solutions that you throw away. And it doesn't actually help. So there's like an optimal, like how much you should reduce the gap. And I experimented a bit, and you can get different run times depending.
So is this related to the fact for the new block, we don't have a good initial choice?
No. I think it's so you're thinking about basically this number, this 20 to 80, like it shouldn't be that many because you're kind of starting close. Is that what you're thinking?
Yes. So I would imagine if you can put a good initial choice for the new sampling point, it should be fast. Why it's not fast?
Right. I have tried reusing little x as much as I could, and it turned out to be terrible. I remember. I think SDPB would get stuck essentially. I don't essentially start a little away.
For example, if it's a single correlator, capital X is related to the value of alpha dot f, right? So I would imagine that should be a good choice for the new entries based on.
Wait, so capital X will have, so if you're at a if you're at a point which is negative now, and you've just set a constraint there, then it will probably be 0 or close to 0. And this other point that used to be 0 is not going to be 0 anymore. And so I think you can't start right at the old solution, because you're gonna end up being too close to the old solution, and you need to get to the new solution. So you gotta project yourself up a little, and then you can travel down.
But this is a known problem, right? I mean, we are using an interior point solver, which is just not very nice for hot starting.
Yeah,
we've been saying this for a while now. I think we might really, here especially because you're solving a sequence of semi-different programs that are all very close to each other. So I think we really should aim for a semi-definite solver that can use hot starting. Because it's, I think, and then this number of SDPB iterations hopefully might go down by a factor, especially in the later stages, maybe a factor 10 or so.
Well, I mean, yeah, if it's like 2 to 8 instead of 28, it's still gonna be sort of a similar number of iterations, and then maybe you get a factor 2 faster, which is nice, but it's not like a game changer.
Right, but we might be moving into into a world where we're no longer using polynomial functionals, right? And so then having a solver
you use
that works
polynomials whether you like it or not, right? I mean, I just hide it from you.
Yeah, but we might want to use much more complicated solvers at some point. Where there is no polynomial, you use locally polynomial approximations, right? You don't use
no, I use a global polynomial approximation for the whole thing.
Oh, I see.
Because that's how I compute the mesh. Is I have a essentially Chebyshev approximation for the whole thing to compute the mesh. I mean, when I compute a solution, I'm only computing it at finite points. But in order to find out where it's negative, I have to have some higher order approximation.
Okay.
I tried using just quadratic, and that did not work. You really have to use a much higher order approximation. And
I see. I was intervening to say something about primal dual interior point solvers, but Slava had a question before I intervened, so maybe Slava wants to.
Yeah, I have two questions. So first of all, can it run in feasibility mode, this outer limit solver?
So that would be essentially having a dual gap of 1. So, you know, when you set your initial gap, set it to 1 instead of whatever, and then you've got a solution.
Okay, so
but yeah, so I mean, then you'll get where am I? Oop. Right. Then you'll get this solution, right?
Yeah, so it's interesting to compare also for feasibility runs if this solver, how it compares to SDPB.
I would actually think it should compare well.
Do you also have a certificate of primal feasibility?
Yeah. I get primal and feasible, dual feasibility.
Okay. Because this seems to be very different, potentially kind of different regime. I don't know, it's hard to say. That was the first question. And the second question is, so it was not clear from my previous experience with this methods where you approximate the functional and you look for negative, because we had some similar issues in the C minimization paper, and there we had a particular issue which was slowing us down. So I just wanted to know if you observe anything similar. Is that there was a linear programming algorithm, so quite different, but there we were observing that in final stages of minimization, the algorithm would basically kind of add points. Well, it was not just adding points. There it was kind of shifting from one point to the other.
Yeah, you are moving points around. I don't ever delete points. I only add.
And so for us, it would kind of move points around, and it was causing a big slowdown. But you only add points, and so for you there is no comparable slowdown. So you seem to converge much faster. There's no like fooling around effect.
Well, you know, there's still some whack-a-mole going on where, you know, it's positive here, and then I add a constraint, and then suddenly it becomes negative here, and then I got to add, you know.
But is it a local whack-a-mole or a global one?
So it's mostly local, I'd say. Like in this part.
Yeah,
right?
yeah, here, that's what you were showing.
This is very close, right?
Very close.
And then I had another point, and this is also very close, you know.
So here there was some when in some regional feasibility discussions, which was long ago, we were just discussing this. Then there was some proposal being discussed. It was a long time ago, that when you run into this stage of the, okay, let's call it the whack-a-mole stage. There was a proposal that perhaps at this point you just add kind of a constraint, a quadratic constraint on a small interval.
Right.
rather than just a point-by-point constraint. And then you are kind of course, it's much more expensive, but still
right.
maybe not as expensive. So the question is, would it be? What's your feeling? Would it be? Because that would be kind of a radical way to
solve
this.
So, for the toy problem, right? I mean, you can see, if you added a quadratic constraint between these 2 points, then you'd be kind of done, right? And so I think it would help for this problem, but I feel like in general, like you're gonna have. I feel like in general it's not gonna work, but I'm really not sure.
But I mean, it's definitely going to work. But the question is, would it be more or less expensive than what you are doing? Because it's going to be locally more expensive, but perhaps it will decrease the number of iterations.
Right. Yeah. I mean, then you also have a small matrix that needs to be inverted, which goes to 0, right?
It's something that I don't feel. I don't have.
Is it? But it's
right,
just it's a bigger problem for SDPB to solve at each iteration, right? I don't think it's any different than that.
I mean, it's not a problem to give it to SDPB. It's just it's instead of a constant constraint, it's a polynomial constraint.
It's a polynomial constraint on a small interval, yeah.
Right. It's a and it's a small polynomial, which helps, but it's still, you have a matrix that you have to invert, which is not hard when it's just a 2x2. So maybe that'll be okay. I don't know. I mean, it's not like you're adding a whole bunch of points. You're in terms of number of points, it's not a problem. It's just.
But you're already inverting 2x2 matrices right now in SDPB, right? Because
I'm not inverting. So in outer limits, I'm not inverting singular 2x2 matrices. I invert, you can give it a matrix constraint, but those matrices in general are not singular. It's these polynomial matrices that turn out to be singular because you have a 0, right?
But if you run SDPB to optimality, you're going to get 2 matrices that are both positive semi-definite and their product is 0.
Yes.
So,
that's what I'm saying, is that the those matrices you need to invert.
But you're running SDPB to optimality eventually.
So I have to invert those too, but they're much easier to invert essentially because it's just it's 1 over the number, right? It's a constant constraint. Oh,
sure.
Oh, but you're saying for the 2x2.
At each iteration, you call SDPB with a bunch of 2x2 matrices. And if you do what Slava says, you make
I agree.
These 2x2 matrices become like 4x4.
Yeah, I agree. Yes, there is essentially for the test problem I had, which had 2x2, I have to do a 2x2 inversion.
Yeah.
Which might be part of the reason why I couldn't reduce the precision more than I did. Someone raised their hand.
I have a question. Why moving points is more expensive than add points? Shouldn't that when you're moving points, you have a chance to compute how the block should change? Then it should be cheaper. Why it's more expensive?
So what makes it more expensive is that if you could set a constraint at one point, and then you find that it's negative here, so you move the point over there, and now it's negative over here, and so it just keeps switching, and it doesn't converge.
Okay, thanks.
Mm-hmm.
Right. Going back to the polynomial stuff, you said that the functions need to be evaluated at Chebyshev zeros, and then there's some interpolation that gets done internally.
Yes.
Does that mean that everything will screw up if we try evaluating the blocks themselves, not just their numerators at the Chebyshev zeros?
I don't know what you mean, the blocks themselves. You have values of delta?
Yeah, so usually what we've been doing is writing a polynomial times positive approximation of conformal blocks. So they're rational functions.
Okay.
And if you include the positive prefactor, then there isn't a good polynomial approximation.
Yes. Yes. So yes, you can have a bad polynomial approximation. Yes. And so it may be to your advantage to get rid of that sort of prefactor, but it may not, because without the prefactor, everything blows up, right? Which is one of the reasons you have this prefactor.
Yeah, but it blows up for negative values of delta or of x.
I thought it helps scaling at infinity also. So things tend to go to 0 instead of going to infinity at infinity.
Yeah.
Yeah. So that's where I would see it, is because you evaluate, you evaluate these functions that you need, for example, the 0 of this functional is around 1, but I think for this one I set the interval for sort of evaluating Chebyshev polynomials at 100, so 0 to 100. And so if the numbers are totally whacked at 100, then you're gonna run into problems. And you have to set it pretty big. I mean, I also do interval. I also do a point at infinity to sort of because that turns out to be important. Otherwise, you can't get a high precision result. But you have to have sort of a big enough interval to make sure that you cover all the zeros. And you don't really know where the zeros are, and you can make arguments about the ratio of polynomial coefficients, so that beyond this point there probably we know what the dominant coefficient is, and then you add some factor.
So would you say it's still a bit of an open problem how these should be scaled optimally when they're plugged in?
Yes, I would say it's an open problem, because I haven't used it on enough problems to know whether what I'm doing will work or not for everything. It seems to work for the problems I've done, but I haven't done that many problems.
Thanks.
Mm-hmm. All right. Is anyone else?
Maybe
any other questions?
Okay.
Sava and I had some algorithm to find, well, also in collaboration with others, we had some algorithm to find the local minima of a function along a line. Right. I think I used it in the mathematical.
Right. I think I remember. Yes. You had a method for doing that.
But that's not the critical point right now about.
Yeah.
So even if we change to another algorithm to find minima, that's not what's slowing Walter down.
Yeah.
Mm-hmm.
So even if his algorithm is not maybe only limited to polynomials for now and so on, but that's not. So I mean, given the calculation that Walter you showed that there's like 28 iterations and 20/80 internal iterations, these numbers seem to be very reasonable. So I don't see how one can hope to do better than that. So it seems like the only way to improve things seem to be on the precision side. Like suppose that we lower the precision to what, 64 bits.
Wait, 64 or 53 bits? If I can lower it to 53 bits, suddenly everything is 50 times faster.
Okay.
So that's what I was trying to do.
Yeah.
But I couldn't quite get there.
In all this, are we not worried that the linear programming didn't work with machine precision, Sava?
Wait, I thought the linear programming did work.
Invert summation. No, it didn't work with the needed, but because linear programming also inverted some matrices.
It did? I remember running that problem with double precision. I thought it worked.
No, the continuous the continuous linear programming algorithms that we use in the minimization paper, they did involve inverting some badly conditioned matrices. because basically everywhere near the close to the minima of the so there maybe this problem is also affecting you. So what was happening is that there in the linear programming, the bad conditioning was appearing because as the algorithm was proceeding and the functional was taking its final shape with its minima, the minima were resolved by putting two operators very close to the minimum, and which were getting closer and closer to each other. And it's the small difference. So there were 2 points in the spectrum which were very close to each other, and it's the small difference between these 2 points which was creating bad conditioning in some matrices which needed to be inverted. So yeah.
Okay, so you're saying that just having 2 points close to each other was a problem.
Yeah, that was the problem. And there were many minima with many points very close to each other, which were getting closer and closer as the algorithm was proceeding. So something like that is happening for you as well.
Yeah, so that's essentially, you have 2 rows which are essentially the same.
Yeah.
I don't think that should be a problem, but
no, but so you're feeding. Well, maybe it's not the problem for SDPB solver, but for the simplex method, it was a problem.
Okay.
Yeah. Which we solved using multiple precision. But for your algorithm, I'm not. First of all, I'm not sure if it's a problem. So if you have 2 constraints, so basically, so as the algorithm proceeds, you have more and more constraints, which are accumulating close to the minimum. But I'm surprised you are, for example, here saying that your algorithm only has 28 iterations.
Yeah.
So it means that you are only adding points 28 times.
Yes.
But probably every time you add more than 1 point.
Yes. Well, so what happens is you reduce the gap, you add 10 points, and then 5 points, and then 2 points, and then 1 point, and then you reduce the gap again. So there's that whack-a-mole going on where
so in the end you have many points, and some of these points, so you have every point represents a single constraint, and some of these points are pretty close to each other.
Yes.
So now I am not sufficiently don't have at my fingertips SDPB algorithm, so I don't know if this causes some bad conditioning somewhere. The fact that you have 2 constraints, which are, I think you should have, because in the old days people said, oh no, you shouldn't add 2 constraints to SDPB, which are secretly the same, because this will cause bad conditioning. So you better work out that all constraints should be independent, people said in the old times. So this means that if you have 2 constraints which arise from very close deltas, then somewhere it's going to cause bad conditioning. It's almost the same, and it should cause bad conditioning somewhere.
Yeah, people still say that in modern times, I think.
Yeah, people say so. So this suggests that maybe indeed in such a situation, when there are 2 points, when there are points accumulating close to each other, then indeed you will be better off from the point of view of conditioning by replacing this whole region where points are accumulating by some small interval where you will just impose a quadratic constraint.
Right. Right.
So
I feel like I have to do experiments because I feel like I've done this experiment and I didn't see the problem, but now I have to verify that.
Let me make a suggestion, because I think this discussion is productive for the people that are really thinking about this problem. So I suggest we just thank Walter again and stop the recording, and then everyone can continue the discussion more freely.
But you shouldn't stop the recording. So I'm happy to keep being the host. I think I'm now co-host, so I can stop the recording when we are done.
Oh, okay. I thought that it would be, if you prefer to keep the recording, no worry.
Oh, well, let's stop the recording. Yeah, let's stop the recording. Maybe Walter will say something off the record.
Okay. And let's just thank Walter.
Yeah.
Thank you very much.
Thanks.
Mm-hmm.